You can settle in now, wherever you are. There's nothing you need to do, nothing you need to remember. This is simply a quiet exploration, a soft wandering through one of the universe's most beautiful mysteries. You might follow along closely, or you might let these words become a gentle rhythm in the background. Either way is perfectly fine. We're going to think together about time, but not in the way you usually think about it, not the time that ticks on clocks or marks the hours of your day. We're going to explore something deeper, something stranger, something that reveals that time itself is far more flexible, far more mysterious than it might seem in ordinary life. This is the story of time dilation, a phenomenon that shows us that time can stretch and compress, that it can move at different speeds in different places, that it is woven into the very fabric of the universe in ways that are both strange and oddly comforting. There's no hurry here. You can let your mind rest. You can let these ideas wash over you like waves, and if you drift away, that's exactly as it should be. Let's begin with something simple, something you already know in your bones. Time feels constant, doesn't it? A second is a second. A minute is a minute. When you're waiting, time might feel slow, and when you're enjoying yourself, it might feel fast. But you know, somewhere deep down, that this is just perception. You know that time itself is marching forward at the same steady pace, always and everywhere, like a great cosmic metronome keeping perfect rhythm. This feeling is natural. It's how humans have understood time for most of our history. It's how time appears to work in everyday life. When you meet a friend for coffee at 3 o'clock, you both arrive at the same 3 o'clock. When you watch a clock, its hands sweep around at a pace that seems absolute, fundamental, unchanging. The universe, in this view, has a single timeline, and everything in existence moves along it together, synchronized, sharing the same present moment, the same now. This is how Isaac Newton understood time. Newton, working in the late 1600s, was one of the most brilliant minds humanity has ever produced. He gazed up at the heavens and saw patterns, mathematical relationships, laws that governed the motion of planets and moons and falling apples. And in his view, time was absolute. He imagined time as something that flowed uniformly, like a river that moved at exactly the same speed everywhere, untouched by anything that happened within it. In Newton's universe, you could imagine a vast cosmic clock, ticking away somewhere beyond the stars, and every other clock in existence, no matter where it was, no matter how fast it was moving, would remain perfectly synchronized with that cosmic timepiece. This is a comforting vision. It matches our intuition. It makes time something solid, something dependable. And for centuries, it worked remarkably well. Newton's physics could predict the motions of planets, could explain tides and trajectories, could send ships across oceans using the stars for navigation. Time, in this framework, was the stage on which the universe performed its drama, but the stage itself never changed, never bent, never responded to what happened upon it. You can just breathe now, softly. There's no need to hold on to any of this tightly. Let it be there, gently, in the background. But then something began to shift. In the 1800s, scientists started noticing something peculiar about light. Light, it turned out, was much stranger than anyone had imagined. When you watch waves moving across water, you can see that they need the water to exist. Sound waves need air, or some other medium to travel through. In the emptiness of space, there is no sound, because there's nothing to carry it. So it seemed natural to assume that light, too, must need some kind of medium, some substance that filled all of space and allowed light to propagate through it. Scientists called this hypothetical substance the ether. They imagined it as an invisible, intangible medium that permeated everything, that filled the universe from the earth to the farthest stars. And if the ether existed, then it should be possible to detect it. After all, the Earth moves through space as it orbits the Sun. If the ether is stationary, then the Earth must be moving through it, the way a ship moves through water. And that movement should create a kind of ether wind, a current that could be detected by carefully measuring the speed of light in different directions. In 1887, two scientists named Albert Michelson and Edward Morley conducted an extraordinarily precise experiment to detect this ether wind. They used mirrors and light beams and interference patterns, tools so sensitive they could detect differences in the speed of light that were incredibly tiny. They expected to find that light traveled at slightly different speeds, depending on whether it was moving with the Earth's motion through the ether or against it, but they found nothing. No matter which direction they measured, no matter what time of day or what season of the year, the speed of light remained exactly the same. It was as if the ether didn't exist at all, or if it did exist, the Earth somehow wasn't moving through it, which made no sense given that the Earth was clearly orbiting the Sun. This was deeply puzzling. Scientists proposed various explanations, various ways to rescue the idea of the ether, but none of them quite worked. The mystery lingered, a strange little crack in the foundation of physics, easy to ignore but impossible to truly explain away. You might feel your thoughts wandering now. That's perfectly natural. You can let them wander. There's nowhere you need to be, nothing you need to figure out. And then came Albert Einstein. Einstein was a young man working in a patent office in Switzerland in the early 1900s. He wasn't a university professor. He didn't have access to fancy laboratories or research funding, but he had a brilliant, curious mind, and he loved to imagine things, to play with ideas, to think deeply about the nature of reality. Einstein looked at the puzzle of light and the ether, and he made a radical choice. Instead of trying to explain away the strange results of the Michelson-Morley experiment, instead of trying to salvage the old ideas, he simply accepted what the experiment seemed to be saying. Light always travels at the same speed, he proposed, no matter how you're moving, no matter what you're measuring it relative to. This was his starting point, his foundation. The speed of light, he said, is a cosmic speed limit, an absolute constant of nature, roughly 186,000 miles per hour, 300 million meters per second. Every observer, everywhere, moving at any speed, would measure light moving at exactly this speed. This might sound simple, but its implications are staggering, reality-bending, profound. If the speed of light is constant for everyone, then something else must give. And what gives, Einstein realized, is space and time themselves. Let yourself rest with this idea for a moment. There's no pressure to understand it completely. Just let it be there, like a soft presence in the room. Imagine you're standing still and you shine a flashlight forward. The light races away from you at the speed of light, naturally. Now imagine your friend is on a train moving past you very quickly, and she also shines a flashlight forward. How fast is her light moving? Your intuition, based on everyday experience, would say that her light should be moving faster than yours, because she's already moving forward, and the light should add that motion to its own speed. The way a ball thrown from a moving car moves faster than a ball thrown from a stationary one. But Einstein said no. Your friend's light is also moving at exactly the speed of light, the same speed as yours, no faster. This seems impossible. How can both beams be moving at the same speed when one of them started from a moving source? The answer, Einstein realized, is that time itself must be different for you and your friend. If she's moving very fast, time for her must be passing more slowly than time for you. From your perspective, her clock is ticking slower, her heartbeat is slower, her thoughts are unfolding more gradually. This is time dilation. It's not an illusion or a trick of perception. It's a real physical difference in the rate at which time flows. You can let this settle gently. You don't need to grasp it all at once. We'll return to this idea again and again, circling it slowly, letting it reveal itself in layers. Einstein published his special theory of relativity in 1905. It was a short paper, elegant and radical, and it changed everything. The word relativity refers to the fact that motion is always relative. You're never simply moving. You're moving relative to something else. If you're sitting still right now, you're still relative to the ground beneath you, but you're also moving very fast, relative to someone on the other side of the earth, because the earth is spinning. And you're moving even faster relative to the sun, because the earth is orbiting. There's no absolute rest, no privileged reference frame where you can say this is truly stationary. And because motion is relative, time must be relative too. Your time and someone else's time will match only if you're at rest relative to each other. The moment you start moving at different speeds, your times begin to diverge. This is strange. It violates our intuition. But it's true, and we can explore why, gently and without pressure, letting the understanding unfold naturally. Think about what it means to measure time. A clock is really just a device that counts regular events. A pendulum swings back and forth. A quartz crystal vibrates. Light bounces between mirrors. We count these events, and we call that time. 1 second is defined by a certain number of oscillations of a particular kind of light emitted by cesium atoms. Time, in a sense, is motion. It's change. It's the unfolding of events. Now imagine the simplest possible clock. Picture two mirrors facing each other, perfectly parallel, with a beam of light bouncing back and forth between them. Each round trip of the light is one tick of the clock. If the mirrors are, say, 1 foot apart, and light travels at the speed of light, then each tick takes a very tiny amount of time, but it's regular and predictable. You're holding this clock, standing still. The light bounces straight up and down, tick, 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 perfectly vertical. Now imagine your friend is moving past you at an enormous speed, carrying an identical clock. From your perspective, watching her zoom by, what does her clock look like? The light in her clock is still bouncing between the mirrors. But because she's moving, the path of the light from your perspective isn't straight up and down anymore. The light has to travel diagonally. It goes up and forward, then down and forward, tracing out a zigzag path as the clock moves along with her. But here's the key. The light still has to travel at the speed of light. That's the cosmic rule. The fundamental constant. It can't go any faster. So if the light is traveling a longer path, a diagonal instead of straight up and down, but it's moving at the same speed, then it must be taking more time to complete each bounce. From your perspective, her clock is ticking slower than yours. Time for her is passing more slowly. There's nothing wrong with her clock. It's working perfectly. And from her perspective, from inside her own frame of reference, her clock seems completely normal. It's ticking at exactly the rate she expects. In fact, from her point of view, you're the one who's moving, and your clock is the one that's ticking slowly. Both perspectives are valid. Both are true. Time is not absolute, it's relative. It depends on your frame of reference, on how you're moving. You can close your eyes now, if you like. You can let these images form gently in your mind, or you can let them fade into softness. There's no wrong way to experience this. This is time dilation. It's a stretching of time, a slowing of clocks, that happens whenever objects are moving relative to each other at very high speeds. In everyday life, you never notice it, because everyday speeds are far too slow. When you drive a car, or ride a bike, or even fly in an airplane, you're moving at speeds that are absolutely tiny compared to the speed of light. The time dilation that occurs is real, but it's so minuscule that even the most precise clocks can barely detect it. But when speeds become substantial, when they start to approach a significant fraction of the speed of light, time dilation becomes dramatic. If you could travel at 90% of the speed of light, time for you would pass at less than half the rate of time for someone standing still. If you traveled for what felt like 1 year to you, more than 2 years would pass for them. At even higher speeds, the effect becomes more pronounced. At 99% of the speed of light, time dilation increases further. At 99.9%, further still. As you approach the speed of light, time for you slows down more and more dramatically relative to the outside world, stretching and stretching, approaching a limit where, if you could somehow reach exactly the speed of light, time for you would stop entirely. But you can't reach the speed of light, not if you have mass. Only light itself can travel at the speed of light. For anything with mass, getting closer and closer to light speed requires more and more energy, and reaching it would require infinite energy, which is impossible. The speed of light isn't just fast. It's a fundamental boundary, a cosmic limit that cannot be crossed. Let this settle. Let yourself feel the strangeness of it, the quiet wonder. Time can stretch, time can slow. It's not fixed, it's not absolute. It's woven into the universe in a way that responds to motion, that bends and flexes, depending on how fast you're traveling. You might be wondering how we know this is true. It sounds like theoretical speculation, like abstract mathematics, like something that might be interesting to imagine, but not necessarily real. But time dilation is not speculation. It's been measured, tested, confirmed in countless experiments over more than a century. One of the earliest confirmations came from studying particles called muons. Muons are created high up in Earth's atmosphere when cosmic rays, high-energy particles from space, collide with atoms in the air. Muons are unstable. They decay, falling apart into other particles very quickly. On average, a muon at rest lasts only about 2/millionths of a second before it decays. Given how short their lifespan is, muons created in the upper atmosphere shouldn't be able to reach the ground. Even traveling at nearly the speed of light, they should decay long before they complete the journey. And yet, when scientists set up detectors on the Earth's surface, they found muons arriving in large numbers, far more than should be possible if time were absolute. The explanation is time dilation. The muons are moving at speeds very close to the speed of light. From our perspective, watching them fall through the atmosphere, their internal clocks are ticking very slowly. What feels like 2/millionths of a second to them corresponds to a much longer period of time for us, long enough for them to reach the ground before they decay. From the muons' perspective, something different is happening, but the result is the same. From their point of view, they're at rest, and the Earth is rushing up toward them at nearly the speed of light. But in their frame of reference, the atmosphere is contracted, compressed, much thinner than we measure it to be. This is another consequence of relativity, related to time dilation. Space itself contracts in the direction of motion. So from the muons' perspective, the journey to the ground is much shorter, short enough to complete in their brief lifetime. Both perspectives are correct. Both predict the same outcome. The muons reach the ground, and the reason they can is time dilation, a real, measurable stretching of time. You don't need to hold on to all these details. Let them drift. Let them be present without effort. The universe is strange and beautiful, and you're safe here, thinking about it softly. Time dilation has been confirmed in many other ways. Scientists have flown extremely precise atomic clocks on airplanes, and when they returned and compared them to identical clocks that stayed on the ground, they found that the flying clocks had ticked slightly slower. The difference was tiny, measured in billionths of a second, but it was exactly the amount predicted by Einstein's equations. Today, time dilation is not just a curiosity, it's a practical necessity. The Global Positioning System, GPS, which helps you navigate when you are driving or walking, depends on satellites orbiting the Earth. These satellites carry extremely precise atomic clocks, and they constantly broadcast the time. Your GPS device receives signals from multiple satellites, compares their timestamps, and uses the differences to calculate your exact position. But the satellites are moving at high speeds relative to the ground, and they're also farther from Earth's gravity, which affects time in another way we'll come to shortly. Both of these effects cause the clocks on the satellites to tick at slightly different rates than clocks on the ground. If this time dilation weren't accounted for, if the system didn't continuously correct for it, GPS would quickly become wildly inaccurate, drifting by miles within just a day or two. So every time you use GPS, you're relying on Einstein's theory of relativity. You're relying on the reality of time dilation. It's built into the technology, invisible but essential, a quiet confirmation that time truly is relative. Let yourself breathe deeply now. Let these ideas exist in the background, not demanding attention, just there, like stars in a dark sky. What Einstein discovered in 1905, with his special theory of relativity, was profound. But it was only the beginning. Special relativity dealt with objects moving at constant speeds, traveling in straight lines through empty space. It didn't address gravity. It didn't explain what happens when objects accelerate, or when massive objects like planets and stars curve space around them. Einstein spent the next 10 years thinking about these problems, and in 1915 he published his general theory of relativity, a work of even greater depth and beauty. General relativity revealed that gravity itself is a consequence of the curvature of space-time, and that this curvature also affects the flow of time. Space-time is a concept that merges space and time into a single unified fabric. In everyday language, we think of space as the three-dimensional arena where things happen, and time as the separate dimension that marks when they happen. But Einstein showed that space and time are intimately connected, woven together into a four-dimensional whole. Events don't just happen in space, and they don't just happen in time. They happen in space-time at specific points that have both spatial and temporal coordinates, and space-time is not rigid, it's flexible. It can bend, warp, and curve in response to the presence of mass and energy. Massive objects like stars and planets create curves in space-time, and these curves are what we experience as gravity. Imagine space-time as a vast, stretched rubber sheet. If you place a heavy ball on the sheet, it creates a dip, a curved depression. If you roll a smaller ball nearby, it will curve toward the heavy ball, not because the heavy ball is pulling on it directly, but because the sheet itself is curved. The smaller ball is simply following the geometry of the curved surface. This is how gravity works. The Earth curves space-time around it, and the Moon follows the curves in space-time, orbiting the Earth. The Sun curves space-time even more dramatically, and the planets orbit along the curved paths that result. There is no force reaching across empty space. There is only the shape of space-time itself, guiding the motion of objects. You can rest with this image. You can let it be simple and visual, not worrying about the mathematics or the precision. The universe is made of shapes and curves, and time flows along with them. Here's the remarkable thing. When space-time curves, time curves too. Time flows at different rates, depending on where you are in the gravitational field. The deeper you are in a gravitational well, the more space-time is curved, and the more slowly time passes for you relative to someone farther away. This is gravitational time dilation. It's different from the time dilation caused by motion, but it's equally real, and it arises from the same underlying structure of space-time. If you're standing on the surface of the Earth, you're at the bottom of a gravitational well created by the Earth's mass. Time is passing slightly more slowly for you than it is for someone in a spaceship far out in space, far from any massive object. The difference is small for the Earth, because the Earth is not particularly massive compared to stars or black holes, but it's measurable. Clocks at sea level tick slightly slower than clocks on a mountaintop, because the mountaintop is farther from the Earth's center, and therefore experiences slightly weaker gravity. This effect has also been measured directly. In 1971, scientists conducted an experiment where they flew atomic clocks around the world on commercial airliners. When they brought the clocks back and compared them to identical clocks that had remained stationary, they found tiny differences. Some of the differences were due to the motion of the planes, as predicted by special relativity, but some were due to the changing gravitational field, as predicted by general relativity. The clocks had ticked at different rates, depending on their altitude and speed, and the measurements matched Einstein's predictions beautifully. Gravitational time dilation becomes much more dramatic near very massive objects. Near a neutron star, where gravity is enormously strong, time would pass noticeably slower than it does here on Earth, and near a black hole, the effect becomes extreme. A black hole is a region of space-time where gravity is so strong that not even light can escape. It forms when a massive star collapses at the end of its life, compressing its mass into an incredibly small volume. The gravitational field near a black hole is so intense that space-time curves almost infinitely steeply, creating a boundary called the event horizon. Anything that crosses the event horizon is lost forever, pulled inexorably toward the singularity at the center, unable to escape even if it travels at the speed of light. Near the event horizon of a black hole, time dilation becomes almost unimaginable. If you were to watch a friend fall toward a black hole, you would see them slow down as they approached the event horizon. Their movements would become more and more sluggish from your perspective, their clock ticking slower and slower. As they reached the horizon, they would appear to freeze, asymptotically approaching the boundary but never quite crossing it, at least not in your frame of reference. Time for them would stretch out toward infinity relative to you. From their perspective, though, nothing special would happen at the event horizon itself. At least, not at first. They would simply fall through, continuing on their journey toward the singularity. But their experience of time would be dramatically different from yours. What feels like a moment to them might correspond to years or centuries passing for you, far away from the black hole. You can let your mind wander across this vast landscape of possibilities. You don't need to understand the mechanics perfectly. Just feel the strangeness, the beauty of it, the way time is not one thing but many things, flowing at different rates in different places. Time dilation is not just about clocks or measurements. It has profound implications for the nature of reality, for the way we understand existence itself. It means that there is no single, universal now. The present moment is not the same everywhere. When you think about what is happening right now on a distant planet, the question doesn't have a simple answer. It depends on your frame of reference, on how you're moving, on where you are in a gravitational field. Two events that seem simultaneous to you might not be simultaneous to someone else moving at a different speed. The order of events can even be ambiguous in certain situations. If two events are far apart, and neither can causally influence the other, meaning no signal traveling at the speed of light or slower could connect them, then different observers can disagree about which event happened first. One observer might see event A before event B. Another, moving differently, might see event B before event A. Both perspectives are equally valid. This doesn't mean that causality is violated. Events that are causally connected, where one can influence the other, maintain their order for all observers. The universe is consistent in that way. But the notion of a single absolute timeline that everyone shares is an illusion. Time is local, personal, dependent on your path through space-time. Let this idea settle softly. Let it be something you notice rather than something you figure out. The universe is more fluid than it seems. There's a thought experiment, a story that Einstein himself used to think about these ideas, often called the twin paradox. It goes like this. Imagine two twins, identical in age. One twin stays on Earth, while the other boards a spaceship and travels at an enormous speed to a distant star, and then returns. For the twin on the spaceship, traveling at speeds close to the speed of light, time passes normally from their own perspective. They might experience the journey as taking, say, 10 years, but because they're moving so fast, time dilation occurs. The clocks on their spaceship tick more slowly relative to Earth time. When the traveling twin returns, they find that far more than 10 years have passed on Earth. Maybe 20 years, or 50 years, or even more, depending on exactly how fast they traveled. The twin who stayed home has aged significantly more than the twin who traveled. They're no longer the same age. The traveler has moved through time differently, has experienced fewer heartbeats, fewer breaths, fewer moments, even though both twins' lives unfolded naturally from their own perspectives. This is not a paradox, though it was called one early on because it seemed contradictory. It's a real consequence of time dilation, one that would genuinely occur if such a journey were possible. The traveling twin doesn't feel like time is passing slowly. They don't notice anything unusual. But when they compare their clock, their calendar, their age to their siblings, the difference is undeniable. This scenario has a name sometimes: time travel into the future. The traveling twin has, in a sense, traveled forward in time, arriving in their siblings' future without experiencing all the moments in between. It's not time travel in the science fiction sense, with machines that jump discontinuously through time, but it's real. And it's possible in principle, limited only by the practical challenge of achieving speeds close to the speed of light. You can imagine this gently, without urgency. Imagine the reunited twins, one older, one younger, both having lived genuine lives, but through different flows of time. It's strange and poignant, and somehow beautiful. Time dilation also has implications for the very concept of aging. Aging is a biological process, driven by chemical reactions, cellular processes, the accumulation of damage and entropy in living systems. All of these processes unfold in time. If time itself is passing more slowly for you, then all these processes slow down proportionally. Your heartbeat slows. Your cells divide more slowly. Your thoughts unfold more gradually, all from the perspective of someone in a different frame of reference. From your own perspective, you always experience time normally. A second always feels like a second to you, but the relationship between your time and someone else's time can vary. This means aging itself is relative. Two people who start at the same age can end up at different ages, can have experienced different amounts of subjective time, if their paths through space-time differ. This is not anti-aging in any practical sense. You can't slow your own experience of aging from your own perspective through time dilation. But you can, in principle, age more slowly relative to the external world, relative to people you've left behind. There's a melancholy to this, a loneliness. The traveling twin returns to find that everyone they knew has aged, or perhaps even passed away. They've preserved their own youth at the cost of losing synchrony with their world. It's a trade-off that exists only in the realm of near-light-speed travel, but it's a real one, woven into the structure of space-time. You can let your thoughts drift here. There's no need to dwell on sadness or loss. Just notice the strangeness, the way time is personal, the way it connects us, and also separates us in ways we don't encounter in everyday life. Let's return, gently, to the question of why. Why does time dilation occur? What is it about the universe that makes time flexible? The deepest answer comes from the structure of space-time itself, from the way space and time are unified. In space-time, every object, every particle is always moving. Even if you're sitting perfectly still, not moving through space at all, you're still moving through time. You're aging, experiencing moments, progressing from past to future. In the mathematics of relativity, there's a quantity that remains constant for any object, a kind of speed through space-time. You can think of it as your total velocity through the four-dimensional fabric of space-time. When you're at rest in space, all of your motion is through time. You're moving through time at the maximum rate. But when you start moving through space, some of your motion through space-time gets redirected. Instead of moving purely through time, you're now moving through both space and time. And because your total velocity through space-time is fixed, moving through space means you move through time more slowly. The faster you move through space, the slower you move through time. And the total remains constant. This is a simplified way of thinking about it, not mathematically rigorous, but it captures something essential. Motion through space and motion through time are linked, traded off against each other, like two components of a single thing. Light, moving at the speed of light, moves entirely through space and not at all through time. Photons, the particles of light, don't experience time. From a photon's perspective, if it could be said to have one, no time passes at all. A photon is emitted and absorbed in the same instant from its own frame of reference, even if billions of years pass for the rest of the universe during its journey. This is a strange thought, almost impossible to fully grasp. But it hints at something profound. Time and space are not separate. They're different aspects of the same underlying reality. You can rest with this. You can let it be mysterious. The universe doesn't require you to understand it completely. It's enough to sense its shape, its vastness, its strange and subtle beauty. Gravitational time dilation arises from similar principles, but the mechanism is different. When space-time is curved by mass, the paths that objects follow through space-time are altered. Time itself flows along these curved paths. Near a massive object, the curvature is steep, and time flows more slowly relative to regions where space-time is flatter. One way to think about it is that gravity affects the very geometry of existence. Clocks measure the passage of time by counting regular events. But those events unfold within space-time. When space-time is curved, the distance between events, measured in a four-dimensional sense, changes. A second near a black hole corresponds to a longer interval in the geometry of space-time than a second far from any mass. This is abstract, and you don't need to visualize it precisely. The key point is that gravity and time are connected. Where gravity is strong, time is slow. Where gravity is weak, time is fast. This is as fundamental to the universe as the fact that objects fall down, or that light travels in straight lines, or what appear to be straight lines, in flat space. General relativity predicts many strange and wonderful phenomena, and most of them have been confirmed by observation. One of the most dramatic confirmations came from an experiment conducted by two scientists, Arthur Eddington and his colleagues, in 1919. They observed a total solar eclipse and measured the positions of stars near the sun in the sky. According to general relativity, the sun's mass should curve spacetime around it, and this curvature should bend the paths of light rays passing near the sun. Stars that appear close to the sun in the sky should seem to shift slightly from their usual positions, because the sun's gravity bends the light coming from them. Eddington's measurements confirmed this prediction. The starlight was indeed bent, by almost exactly the amount Einstein had calculated. It was one of the first major pieces of evidence that general relativity was correct, and it made Einstein famous worldwide almost overnight. The idea that mass could bend light, could warp space itself, captured the public imagination and changed how humanity understood the universe. Since then, countless other observations have confirmed general relativity. We've observed the precession of Mercury's orbit, a tiny deviation from Newton's predictions that general relativity explains perfectly. We've detected gravitational waves, ripples in space-time itself produced by colliding black holes and neutron stars, traveling across the universe at the speed of light. We've photographed the shadows of black holes, seeing the silhouettes of event horizons against the glowing gas around them. Every test, every measurement, every observation has confirmed Einstein's vision. Space-time is real. It curves. And time flows differently in different places. Let yourself float through these ideas, not grasping, just drifting. The universe is describing itself to you through these words, and there's no pressure to capture it all. Time dilation invites us to think about time in new ways. We often think of time as something external, something that exists independently of us, a river we're carried along by. But relativity suggests that time is more intimate than that. Time is part of the structure of the universe, but it's also part of your personal experience, your trajectory through space-time. Your time is your own, shaped by how you move, where you go, how deeply you're embedded in gravity's embrace. This has philosophical implications. It raises questions about what it means to exist, to be present, to share a moment with someone else. If time can differ from person to person, what does it mean to be simultaneous, to be together in the now? In everyday life, these questions don't matter. Time dilation for ordinary speeds and ordinary gravity is so small that everyone on Earth experiences time at almost exactly the same rate. The differences are measured in billionths of a second over a lifetime, imperceptible and irrelevant for practical purposes. We can live as if time is absolute, as if we all share the same present moment, and we'll never notice the tiny discrepancies. But in the universe at large, where speeds can be enormous and gravity can be crushing, time dilation is not a small effect. It's a dominant feature of reality. Astronauts on the International Space Station experience time slightly differently than people on the ground. Satellites must account for time dilation to function. Near black holes or neutron stars, time becomes so distorted that it barely resembles the steady, uniform flow we're familiar with. And this raises a question: which time is real? If time can flow at different rates, is there a true rate, a correct time? The answer, according to relativity, is that all times are equally real. There is no privileged perspective, no correct frame of reference. Your time is as valid as anyone else's. The universe doesn't have a preferred clock. This is called the principle of relativity, and it's at the heart of Einstein's theories. The laws of physics are the same for all observers, regardless of how they're moving. No one is stationary in an absolute sense. No one's time is the right time. All perspectives are valid, and the universe accommodates them all. You can let this principle wash over you. It's a strange kind of equality, a democracy of perspectives, where no viewpoint is privileged, no experience is more real than any other. There's a beauty to this. It means that your experience of time, of existence, is fundamentally real. You're not measuring time incorrectly if your clock differs from someone else's. You're simply experiencing space-time from your own unique path through it. The universe is vast enough, flexible enough, to contain all these different times, all these different perspectives, without contradiction. Time dilation also connects to other strange phenomena in relativity. There's length contraction, the way distances shrink in the direction of motion when you're moving at high speeds. There's the relativity of simultaneity, the way events that seem simul to one observer can be separated in time for another. There's the equivalence of mass and energy, Einstein's famous equation. E equals mc squared, which shows that mass and energy are interchangeable, two forms of the same underlying thing. All of these phenomena are woven together, part of the same tapestry. Spacetime is not a passive stage. It's an active, dynamic structure that responds to mass, to energy, to motion. And time is part of that structure, flowing and bending and stretching along with space. Let's think, softly, about what time dilation means for the universe as a whole. The universe is vast, almost incomprehensibly so. Light from distant galaxies takes billions of years to reach us. When we look at those galaxies through telescopes, we're seeing them as they were in the distant past, because the light has been traveling toward us for so long. But time dilation complicates this picture. As the universe expands, galaxies move away from each other, and distant galaxies move away from us at enormous speeds. Because of time dilation, time in those distant galaxies is flowing differently than time here. The universe doesn't have a single, universal time. Every region of space has its own local time, and these times relate to each other in complex ways. In cosmology, the study of the universe as a whole, scientists define something called cosmic time, a kind of average time that represents the age of the universe from a particular perspective. But this is a convenience, a simplification. The actual flow of time varies from place to place, and the universe is a patchwork of different times, all unfolding together, all equally real. This is a dizzying thought. The universe is not just vast in space, it's vast in time, and that vastness is not uniform. Some regions have experienced more time than others. Some clocks have ticked more, others less. And all of this is part of the natural order, the way space-time works when you account for relativity. You can let yourself feel small in the face of this vastness, but not in a diminishing way. You're part of this universe, part of this intricate web of space-time. Your experience of time is as real and valid as any other, a unique thread in the fabric of existence. Time dilation also invites us to think about the future. If humanity ever develops the technology to travel at speeds close to the speed of light, time dilation will become a practical consideration. Journeys to distant stars might take decades or centuries from the perspective of Earth, but only years or months for the travelers. This could allow exploration of the galaxy, but it would come with profound costs. Travelers would be severed from their own time, unable to return to the era they left behind. This is sometimes called the interstellar time lag. It's not a technological problem. It's a fundamental feature of space-time. Any civilization that spreads across the stars will have to grapple with it. Different worlds, different ships, will exist at different times, in a sense, unable to share the same present moment. Some scientists have speculated about using time dilation deliberately as a way to survive into the future. If you could travel very fast, you could age slowly while the universe ages quickly around you, effectively leaping forward in time. You could see the future, experience it firsthand, without waiting through all the intervening years, but you couldn't go back. Time dilation allows travel into the future in a sense, but not into the past. The flow of time, from past to future, is one-directional. This is called the arrow of time, and it's one of the deep mysteries of physics. Why does time flow in one direction? Why do we remember the past, but not the future? Why does entropy increase? Disorder spread? Why do things break down rather than spontaneously reassemble? These questions go beyond time dilation, into thermodynamics, quantum mechanics, the nature of causality. But they're connected. Time is not just a dimension, it's a process, a flow, an unfolding. And time dilation shows us that this flow is not uniform, not absolute but relative, flexible, responsive to the structure of space-time. You don't need to solve these mysteries. You can let them exist as questions, as invitations to wonder, to think gently about the nature of reality. Let's return, once more, to the experience of time. You're experiencing time right now, moment by moment. Thoughts arise, sounds occur, sensations come and go. This is your personal, subjective time, the flow of your consciousness through existence. Physics tells us that this flow is not separate from the universe. It's embedded in space-time. The moments you experience are events in space-time, points on your unique path, your world line, through the four-dimensional fabric of reality, and because of time dilation, your world line might curve differently than someone else's. If you moved very fast, or if you spent time near a black hole, your path through space-time would be different. You would experience fewer moments, fewer heartbeats, fewer breaths, per unit of external time. But each moment would still feel the same to you. A second would still feel like a second. The flow of your consciousness would remain steady from your own perspective. Time dilation is not something you feel from the inside. It's something that emerges in comparison, when you relate your time to someone else's, when you reconnect after having followed different paths. This is a subtle but important point. Time dilation doesn't change your subjective experience of time. It changes the relationship between your time and external time. You always age at the same rate from your own perspective, but from someone else's perspective, your clock might be ticking slowly, your aging might be slowed, your life might be stretched out. In a sense, everyone experiences their own time as normal, as flowing at the rate of 1 second per second. But the connections between different people's times, the translations between different frames of reference, are where time dilation appears. This is comforting, in a way. No matter what happens, no matter how fast you move or how deep into a gravity well you go, time will always feel normal to you. You'll never experience time as frozen or stretched from your own perspective. The universe ensures that your experience remains consistent, even as the relationships between different experiences become complex. Let yourself breathe deeply. Let yourself feel the passage of time, the steady rhythm of your own existence, the moments unfolding one after another. This is your time, and it's real, and it's yours. Time dilation is one of the most beautiful and strange discoveries in all of science. It reveals that the universe is far more subtle and interconnected than our everyday experience suggests. Space and time are not separate, fixed backdrops. They're dynamic, flexible, woven together into a single fabric that can bend and stretch and curve. This discovery came from pure thought, from Einstein's ability to imagine, to take simple principles to their logical conclusions, to trust the mathematics even when it led to conclusions that seemed impossible. He had no experimental evidence when he first proposed special relativity. He simply believed that the speed of light must be constant, and he followed that belief wherever it led, and it led to a complete reimagining of time, space, and reality itself. It led to the understanding that nothing is absolute, that everything is relative, that the universe is far stranger and more beautiful than anyone had imagined. Since Einstein, we've learned even more. We've discovered that quantum mechanics, the physics of the very small, also complicates our understanding of time. We've found that time might be emergent, not fundamental, that it might arise from more basic processes at the quantum level. We've speculated about the possibility of closed time-like curves, paths through space-time that loop back on themselves, allowing time travel to the past under certain exotic conditions near rotating black holes. But these ideas are still speculative, still uncertain. What we know for sure is time dilation. It's been tested, measured, confirmed, used in technology. It's as real as gravity, as solid as any scientific law we have, and it tells us something profound. Time is not what we thought it was. It's not a simple, universal river carrying everything forward at the same rate. It's a personal experience, a local phenomenon, a property of your path through space-time. It connects you to the universe in ways that are intimate and strange. You can let this be enough. You don't need to understand every detail, every equation, every implication. You can simply know that time is flexible, that it can stretch and slow, that the universe is more mysterious than it seems. As we come toward the end of this exploration, let's rest in the wonder of it all. You've traveled with me through ideas that took humanity centuries to discover, that required the greatest minds our species has produced. You've encountered concepts that violate intuition, that challenge everything everyday experience teaches us about time. And yet, somehow, it all holds together. The universe makes sense, even though that sense is strange. Time can dilate, can flow at different rates, can be relative and personal, and yet causality remains, logic remains, the laws of physics remain consistent. The universe is not chaotic. It's intricate, subtle, profound. You might forget the details of what you've heard tonight. That's perfectly fine. You might remember only a feeling, a sense of strangeness and wonder, a vague awareness that time is more flexible than it seems. That's enough. You might remember nothing at all, and that's fine too. These ideas will have passed through your mind, a gentle presence, a soft rhythm, a voice in the dark. Time itself continues, moment by moment. Your time, flowing at its own rate, carrying you forward through your unique path in space-time. And somewhere, in the universe, other times are flowing too, faster or slower, connected to yours by the beautiful, flexible fabric of space-time. You can close your eyes now, if they're not already closed. You can let yourself drift. You can let time carry you forward gently, softly, into rest. The universe is vast and strange and beautiful. Time is a river with many currents, flowing at different speeds in different places, all part of the same great ocean of existence. You are traveling through it, moment by moment, your own time as real as anyone else's, your path through space-time uniquely yours, and that's enough. That's everything. You can rest now, knowing that you exist in this vast, flexible, mysterious universe, where time itself bends and stretches, where the fabric of reality is more wonderful than anyone ever imagined. Let yourself drift. Let yourself rest. There's nothing more to hold on to, nothing more to understand. Just the gentle passage of time, your time, flowing at its own perfect rate, carrying you wherever you need to go.